SymmGrid, superscaling on-robot learning with parallelized symmetries and egocentric, exocentric visual perception. Learning deep reinforcement learning policies directly on robots is known as on-robot learning. Achieving on-robot learning efficiently is a key goal in the robotics community, as it provides robots the ability to learn the world's physics directly and avoid sim-to-real artifacts that can negatively affect a robot's performance in the real world. However, on-robot learning still learns at slow rates. The culprit lies in that each learning step typically requires a real interaction with the physical environment. The problem compounds because current methods extract only a fraction of the signal from each robot interaction, leading to training sessions that can last hours or days. We present SymmGrid, a trajectory-level augmentation framework that uses parallelized symmetries to superscale the data generated from every robot step, turning one physical attempt into hundreds of valid and reward-preserver training samples and egocentric and exocentric visual setups. SymmGrid achieved convergence times as fast as 16.6, 10.9, and 79.3 minutes for peg insertion, cable routing, and object relocation, and average times of 20, 18, and 90 minutes with a near 100% success rate. Prior work has exploited symmetries as data augmentation or equivariant networks. Whether reflections, rotations, or dihedral and Euclidean groups, these accelerate reinforcement learning by generating extra training data for each robot interaction. However, these methods extract only a handful of symmetry variations per transition. The number of usable symmetries for a single robot interaction has remained a significant bottleneck on learning speed. SymmGrid reframes the Markov Decision Process as a tree where each state-action pair becomes a vertex and an edge. At every time step, we apply parallelized affine transformations to the pair. These transformations create a k by k grid of symmetric equivalences. Each one is then stored as a virtual enactment of the original transition. Consider data superscaling. A single robot state-action transition can produce hundreds of valid transitions, providing an order of magnitude higher data rate than prior image-based methods. And because these transformations are applied at the replay buffer level, SymmGrid can be dropped in as a wrapper directly onto SORL and RLPD without modifying the underlying code. Note that for egocentric setups, our image scenes remain invariant under transformation. For exocentric setups with a fixed global camera, images need to be transformed to depict the expected warping. To this end, we use homographies. We now present 3 on-robot learning experiments. 5 seats of training were conducted directly on the robots. We also evaluated performance across multiple checkpoints, except for object relocation, which was the most expensive. We show video for both training and evaluations for peg insertion, cable routing, and object relocation. Training videos were recorded as time-lapse for more efficient viewing. For evaluations, notice how the policy overcomes disturbances in peg insert, or how different manipulation skills emerge in object relocation. Thanks for watching. To learn more, visit symmgrid-robot.github.io, and extensive tutorials to get you up and running with this work at lipscomb-robotics.notion.site.